we can continue our sections, and the next report, N-foci balls in hyperbolic geometry, presented to Illia Ovtsynov.
Yes.
Please.
So, good afternoon, everyone. My name is Illia Ovtsynov, and I'm going to tell you about N-foci balls in hyperbolic geometry. My supervisor is Doctor of Sciences in Physics and Mathematics, professor, corresponding member of NIS of Ukraine, head of Algebra and Topology Department of Institute of Mathematics of NIS of Ukraine, Maximenko Sergei Ivanovich, and also Doctor of Sciences in Physics and Mathematics, professor of Algebra and Computer Mathematics Department of Taras Shevchenko National University of Kiev, Petrovchuk Anatoly Petrovich. Let's suppose that H2, which is equal to xy, y is greater than 0, is an upper half plane with the Riemannian metric dx squared plus dy squared divided by y squared. It is called a hyperbolic plane and has a constant negative Gaussian curvature -1. Besides, H2 is an Hadamard space, so it is a complete Riemannian manifold of non-positive sectional curvature. And between two any points x and y from H2, there is a unique geodesic sigma xy. It means that we can define a notion of a geodesically convex set in a hyperbolic plane. It is actually a set that for two arbitrary points, x and y, of its sigma xy belongs to this set. Particularly, the mapping rho xy, which is equal to L sigma xy, where L denotes a length of curve in H2, satisfies all the axioms of metric space. So, let's fix in H2 any mutually distinct point x1 and so on, xn, where n is a natural number, and such positive numbers w1 and so on, wna, that the sum of all wk from 1 to n is equal to 1. Open-weighted N-foci ball, or just weighted N-foci ball, is a set A, which consists of all the x from H2, where w1, rho xx1 plus and so on, plus wn, rho xxn is less than A, where x1 and so on xn are called foci of the weighted N-foci ball. A is called a radius of the weighted N-foci ball. Wn and so on wn are called weights of the foci x1 and so on xn. And we can define closed weighted N-foci balls and weighted ellipses the same way, having replaced the symbol less by the symbol less and equal or equal in the previous formula. So the main aim of my work was to research all weighted N-foci balls in the hyperbolic plane and to find out if they were geodesically convex. This question is trivial in the Euclidean space, whereas the same problem is quite difficult in the hyperbolic space. Let's begin with the simplest case, or the case of the standard ball in the hyperbolic plane. Circles in the hyperbolic plane geometrically coincide with Euclidean circle. Yes, if we take, for example, one circle with a hyperbolic center in z or 0 from the complex plane and map it with the function, it is a Möbius transformation, we will obtain an image of this circle in the model of hyperbolic disk where f in z0 is equal to 0. Besides, all the rotations around the coordinate center are isometries of the hyperbolic disk, and from this implies the statement of theorem. And another theorem states that any open ball of a positive radius in the hyperbolic plane is geodesically convex. There are different approaches to the proving of this theorem. For example, one can map the circle from hyperbolic disk with its center in the coordinate center to the Poincare line model of the hyperbolic plane, where all the geodesics are straight like in a Euclidean circle. I was just saying about the second approach to the theorem about the convexity of hyperbolic standard ball. Can I continue?
Yes, yes.
Yes, we know that we can research a usual Euclidean circle in the upper half-plane model. And all the geodesics are either vertical straight lines or arcs of circles with their centers on x-axis. And there is a simple inversion which maps considered model isometrically in itself so that the circle is mapped into another circle, where one concrete geodesic as an arc of a circle becomes a straight vertical line. And we can see convexity of the circle too. And now we are going to prove the general theorem about the convexity of all weighted N-foci balls. And we will require some definitions and some theorems about convex functions on Riemannian manifold. We will call a parameterization gamma of the geodesics between points A and B in H2, where gamma in 0 is equal to A, gamma in 1 is equal to B standard, if for all alpha from the interval from 0 to 1, the equality rho A gamma alpha is equal to alpha L whole. Here L denotes a length of the appropriate geodesic. And a function which maps the hyperbolic plane into the space of real numbers is called convex in a convex set, is for arbitrary points x1 and x2 from R, and a standard parameterization of gamma of the geodesics between them, such that gamma in 0x is x2 and gamma in 1 is x1. Next inequality holds. It is f which maps gamma alpha is not greater than alpha fx1 plus 1 minus alpha fx2. The first theorem states that any finite linear combination of convex functions in Riemannian manifolds, which are all convex, it is convex too. And the second theorem states if a function which maps Riemannian manifold in the space of real numbers is convex in a convex set A, then for all A from R, these sets are convex. Fx less than A and Fx less or equal than A. So let's fix any point x0 which belongs to H2 and define the distance function for it. It has such a notion, and the theorem states that distance function f is convex in the hyperbolic plane H2. And it is worth highlighting that such a function is convex in any other Mars space. But in this work, we got a direct proof of convexity of f for the case of the hyperbolic plane, and it proved that topological and analytical methods often can give more satisfying answer than geometrical one. The important remark is that we didn't research hyperbolic spaces of older dimensions in this work, but they are also other Mars spaces, so this result is true for them too. Having used some isometries of the hyperbolic plane, especially an inversion, it was stated that it is sufficient to discover the function f at the vertical geodesics in the imaginary axis, so that its lower limit equals to I. Then let's assume then that gamma is a standard parameterization of the geodesic. If x0 is in the imaginary axis, it is enough to prove the convexity of this function in this interval, and it proves the convexity of distance function in the hyperbolic plane. But if x0 doesn't lie on the imaginary axis, it is a more complicated function, and it is enough to prove the convexity of this function in 0, 1, and it also states the main result of our work. And from the obtained result implies the next theorem. All open and closed weighted N-foci balls are geodesically convex sets in the hyperbolic plane H2. And it is the main result of our work. I finished.